Welcome back, everyone. Research teams preparing advanced quantum laboratories are controlling the magnetic conditions around their measurement equipment by examining how those conditions form and change. Superconducting magnetic shields are becoming central to this goal because more experiments demand regions that remain stable and have very low noise during operation. In practice, these shields guide magnetic influence away from sensitive components by using materials that maintain strong superconducting behavior at low temperatures. Laboratories planning future upgrades expect these shields to play a larger role because fabrication methods will continue to improve. At this stage, the field shows a shift from conventional shielding approaches toward engineered structures designed for uniform performance. These systems already operate in select demonstration facilities, showing that current deployment is advancing. Upcoming research will aim to refine how their shapes will be formed, so fabrication continues to advance. Quantum groups preparing multi-year equipment plans are identifying shield properties by defining which mechanical behaviors must be supported in next-generation systems. These shields are intended to support more stable measurement conditions as quantum devices become more complex. Researchers expect several fabrication methods to converge toward controlled layering approaches because this convergence improves uniformity in these systems. In this context, the shields appear in early-stage installations today, while wider deployment will remain under development as facilities expand. Teams working toward higher reliability want shield structures that reduce stray magnetic fields and maintain consistent behavior throughout an experiment. This approach sets forward progress while keeping operational detail minimal, so the narrative continues cleanly. The next sections will examine how certain materials are shaped and integrated so the strict requirements of quantum facilities remain supported. Shields used in advanced labs rely on superconducting materials that reach their final performance levels only after being shaped through controlled fabrication steps. Labs focus on mechanical consistency because even small defects alter magnetic behavior and influence performance during experiments. Fabrication involves selecting materials that reach stable superconducting states at accessible cryogenic temperatures and then forming them into structures that direct magnetic influence in a smooth path. At this point, one approach under study uses deposition tools to build layered shells that keep interior regions clean. Another approach uses machined bulk materials prepared to reduce internal stress. Fabrication teams increasingly coordinate with metrology units to verify uniformity, so installation proceeds with fewer uncertainties during setup. A planned phase in upcoming facilities will refine how edge sections will be produced, so later installations improve. Please subscribe. Developers working on shield fabrication are improving deposition systems by adjusting how each layer is applied to complex shapes. These systems allow material to be applied in controlled thickness patterns that help maintain stable superconducting regions once the shield is cooled. In this work, a group at the National Physical Laboratory in Teddington studies how deposition rate changes influence uniformity across curved sections. Their work supports designs that reduce distortions in magnetic flow, so final shield behavior is more predictable. Layering tools now include sensors that track material buildup in real time to keep the layering process stable. Facilities expect next-generation tools to expand the range of geometries that will be fabricated. Machined structures remain important because thick superconducting walls must be shaped through direct cutting processes that control internal stresses. Milling processes must avoid creating stress points that could interrupt superconducting behavior once cooled. A team at the Fraunhofer Institute for Applied Optics and Precision Engineering in Jena evaluates cutting parameters that reduce defect formation. Their studies show that balanced tool forces create smoother surfaces that improve how the shield guides magnetic fields. During machining, strategies now involve monitoring vibrations and temperature drift to protect the physical properties of the material. Future facilities will plan to integrate automated tool correction protocols based on new sensor feedback, so machining remains consistent across long production runs and supports predictable results. These methods help ensure shields maintain stable magnetic environments under varying experiment loads. Some shield designs achieve mechanical stability by combining layered shells with machined support rings that set the physical behavior of the structure. These hybrid structures let engineers manage both thickness and uniformity, while shaping magnetic flow paths in a controlled way that supports stable shield behavior. In this arrangement, fabrication teams at the Massachusetts Institute of Technology in Cambridge are testing controlled bonding techniques that join these components without creating zones that are weak. Their procedures involve applying low-temperature bonding agents and pressing tools that distribute load evenly. The goal is to maintain smooth superconducting transitions throughout the shield so magnetic behavior stays stable during operation. Planned enhancements will include robotic alignment tools that will reduce assembly variation and will improve reproducibility across installations. Quality control programs verify each shield by measuring how its surfaces respond to controlled magnetic inputs. High-sensitivity scanners measure the variation of magnetic response across shield surfaces. During these inspections, a research unit at the University of Oxford uses scanning magnetometers to trace how magnetic influence moves under controlled currents. Their measurements help detect small physical irregularities that could affect quantum experiments if left uncorrected. Fabrication lines now schedule multiple inspection cycles during production to identify issues earlier and to reduce corrections that occur at the end of production. These cycles include low-temperature testing to confirm that superconducting performance is stable. Teams expect future workflows to add automatic correction steps where minor irregularities are polished or adjusted before final assembly. Integrating shields into quantum facilities begins with matching shield geometry to the physical cooling paths used in cryogenic systems. In facility integration, shield geometry must match the cooling paths of dilution refrigerators or other low-temperature devices. Engineers prepare mounting brackets and support frames that hold the shield without adding mechanical strain during cooldown. A development group at the University of Toronto evaluates how frame materials contract at cryogenic temperatures. Their findings guide the selection of components that keep physical alignment during long measurement runs, so the stability of measurements improves. Integration procedures often include staged cooldown tests that verify the shield maintains uniform performance under temperature cycling. These tests help confirm that installed shields support stable quantum measurements over long runs and maintain operational reliability. Future shield designs will use adaptive fabrication that adjusts material thickness in response to predicted magnetic behavior. Developers aim to produce structures where each region supports targeted physical characteristics. Advances in simulation tools make it possible to predict how local variations change magnetic flow. Fabrication teams expect to refine deposition and machining systems so material will be adjusted during production. In planned development, facilities plan to evaluate these adaptive methods in upcoming upgrade cycles, where evaluation will occur as part of planned future work. Successful demonstrations could lead to large-scale adoption across research centers because each center aims to achieve higher quantum stability as development progresses. Efforts to expand shield fabrication capacity begin with training programs that teach technicians how to operate deposition and machining systems within controlled environments. In training operations, these programs teach careful handling of superconducting materials and stress defect prevention. Teams installing shields in upgraded facilities observe that even small variations in handling influence performance and set final reliability levels. Production managers push for standardized protocols that define each fabrication step. A fabrication training group in Stockholm works on documenting these protocols for broader adoption. Their work supports expanding the number of technicians who can produce consistent shield components. This will strengthen the supply chain for facilities planning future expansions by improving the availability of consistent components. Long-term development will focus on achieving higher consistency by comparing how different facilities produce shield batches under shared quality targets. Standardized quality targets allow research centers to share methods and compare performance results under similar conditions. Across these programs, fabrication efforts that use cross-facility benchmarks aim to reduce variation in magnetic response. Technicians working under these guidelines gather data that guide future improvements in deposition control, machining stability, and hybrid assembly. So development continues along a path that remains stable. The next stage of shield evolution will include adapting fabrication lines to demand from larger quantum installations. These developments move the field toward reliable, large-scale superconducting magnetic shielding that supports future quantum installations. Thank you very much for watching. Please like and subscribe.